Então, Richard, tôi là cái tổ. Aku ada tổng cái gì.
It's time 10. It's our scheduled time to start our session. The participants of joining one by one. I hope we will start the session. Let the participants will be allowed to join further. A very good morning. Assalamu alaikum speaker to all the participants and of this today's EICT sponsored FDP session. I feel honored to welcome the speaker, the participants and professors of various institutions for this 13th session of this EICT sponsored FDP program on BioMEMS and LagonChip technologies for point of care applications organized by the Department of Electronic and Communication Engineering, C. Abdul Hakim College of Engineering and Technology, Vellore. So it's our privilege to have another eminent speaker from University Science Malaysia, Dr. Asrulnizam bin Abdul Munaf, with us to deliver his research address on design and fabrication of low-cost microfluidic channel for biomedical applications in this 5-day 13th session of this CICT-sponsored FDP. So before I want to just have a biography of the speaker to be highlighted to the participants. So Dr. Asrulnizam bin Abdul Munaf is Associate Professor and Deputy Director at Collaborative Microelectronic Design Excellence Center, CEDEC, at University Science Malaysia. He is a leader of the CMOS-based sensing interface integrated circuitry, microfluidic-based MEMS, NEMS, and printable-based device technology group at CEDEC. He received his doctoral in engineering from School of Fundamental Science and Technology, Kyoto University, Japan, in 2009. He has authored and co-authored 60 international technical journals and conference and hold 2 patents for his credit. His research interest has been in the areas of microfluidic-based devices, CMOS sensing interface, integrated circuitry, heterogeneous integration, micro 3-dimensional grayscale technology, MEMS, NEMS fabrication technology, printable electronics, and wearable electronics. He received IET JC Bose Memorial Award in 2017 for the Best Engineering Research-Oriented Paper. He is also a senior member of IEEE. So I think we are very lucky and I am very privileged to have such an eminent speaker from University of Science Malaysia in this 15th session. Once again, I welcome you, Dr. Asrul sir. And also I request the participants to be interactive with this session. I hope this session will be a good platform as well as the motivation for the researchers. Once again, I thank you, Dr. Asrul sir. Now I request Dr. Asrul bin Abdul Munaf sir to take over this session and deliver your research address to the participants.
Can I see the screen? Can you make me a
co-host? Yeah, sir. Yeah, sir. I'll be making you the co-host.
Yeah. Assalamualaikum and very good morning. First, I would like thanks to organizers for inviting me to share one of our current research in my group that specific on microfluidic technologies. So I will share what our current research that are related to the development the lab on chip technologies for a biomedical application, and then how we do the integration with microfluidics. Before I start my talk today, let me give me a few minutes to introduce my university, USM, and my centers, and also my research group that I go to deliver a talk with a title on the design and fabrications of low-cost microfluidic channel for biomedical applications. So this is my universities, namely as University Science Malaysia is located at Penang Island. So if you have been in Malaysia, so this the Kuala Lumpur, it take about 45 minutes by flight from Kuala Lumpur to Penang. So this is our university is located at Penang Island. So it's near to the beach, and we consider as a university in gardens. So please, so if you have a chance come to Malaysia, please visit us at Penang Islands. So our university just 15 minutes by car from Penang International Airport. So from Kuala Lumpur, just take 45 minutes by flight and only 4 hours, 3 hours to 4 hours by car. And then we coordinated with Penang Bridge. So this is our location. So where is our centers? So our centers is a location at areas, this area. So that location of our centers. So our center we namely as a collaborative microelectronic design excellence centers, one of the center of excellence under University Science Malaysia. So we only have a postgraduate program. So my center we are focused on the microelectronic engineering, so including the IC designs and the sensors technologies to the embedded system to research activities, and also teaching and learning for a postgraduate program. So our centers top that the location is top on the hill, so that you can have a sea view from our center, I mean from our office, the sea view and also the green view. Yeah. So and then we just 10 minutes opposite with the Equatorial Hotel. So this is a location of our centers. So we are one of the national centers that are focused on the microelectronic engineering activity from the device level, IC design, sensors, and the embedded system engineering. So we also have 4 staff academic and the 7 research officers, and currently we have 15 postgraduate students with us. So this is what our ecosystem. So that is our center. Say that we call as a collaborative microelectronic design excellence centers. Actually, we offer the research and also the training services, including the IC designs training, and also the sensors design. So I mean that all the university in Malaysia, including the private and also the small medium enterprise company, they can access to our servers. And then we provide them the EDA tools in the IC design, such as like Cadence, Mentor, to do the IC design. The same time also we offer a training in a sensors design, and then do the integration with a sensors to work with one system on chip. So we have the design capabilities, and then we work with the Silterra. That means one of our local foundry to do for a chip tap out, the chip fabrication, and then final to the packaging. So this is the ecosystem that we built in the CDEC to serve for the our national agenda. That means to create the ecosystem in IC design and also with a sensors design. So that the role of our centers. So, and this is my lab. So my lab we call as the integrated circuitry and sensor system. So in my lab, we are focused on the development of sensors using the lab on printed circuit board. So we do the sensors. Actually, in my lab, we are focused the three principles of sensing principles: the electrochemical sensing, the FET-based sensing, and the acoustic-based sensing. So all those sensing we are developed on the printed circuit board, such as like the on FR4 and also on the flexible circuit, such as like the TPU and also PET and also for PMIC. So my lab, we promote the technology, how we can fabricate the sensors, the system on printed circuit board. Then we do the integration with the CMOS integrated circuit to be as a sensing interface to amplify the signal from the sensors. So that can be as a hybrid integrations. So we not going to the monolithic integration. So in my lab, we do a promotion. We move forward on the technologies, how can to develop the sensors on the printed circuit board with the multiple version, such like the FR4 or any the flexible electronic like the TPU, the Teflon polyurethane, that can be stretched. So that also on for PMIC, so that we hybrid integration with a CMOS sensing interface. So that what our the core research and activity in my group. So today I really appreciate for invite me. That means to deliver my research in my group. But today I more the explore with all of you what our current research in a microfluidic fabrication using the soft lithography technique. So that is my title for today. So I will explain towards to what the technologies that we use in my laboratory, in my group, mean to develop the microfluidic and how to develop the sensors, and then that how we do the integration. So the title is a design and fabrication of low-cost microfluidic channel for biomedical applications. So this is an outline of my topic. So I will start to overview of the current lab on chip technologies, and then what is a component, what the component is needed to have a full system for the lab on chip technologies, and also and then what the technology, what the fabrication technique that used in my group to develop the microfluidic. So we use the grayscale lithography technique, and how we apply the grayscale lithography to develop optofluidic, microdroplet, micro mixing, and we integration with the lab on PCB to have a one system on PCB. That means to develop the lab on printed circuit board. Right? So this is a lab on chip. So what is the lab on chip? So the lab on chip is the technology how we capable, that means to miniature all the lab apparatus like the petri dish and like a weight and then like a big scale of a mixer. So it means how we be able to transfer all the lab apparatus on a chip. Mean on a single chip, we can be able to have a mixer. That means we no need use like the conventional technique. We need a shaker to do the mixing. So that means how we be able to using the technique, the fundamentals of fluid dynamic like the turbulent flow and laminar flow by do modification of the geometrical dimension and the velocity, how we can create behavior as a mixer, and then how we can using the electrostatic technology to create a micro pump or the micro valve, and then how we can use the technique of the electrochemical sensing as an examples to create the reactor chamber. That means to make it the detection. So the lab on chip is the technology how we be able to transfer the conventional lab apparatus on chip. That can be the monolithic integration. So it means we can make it, the system can be a smaller. So it means we can reduce the sample, we can reduce the waste by reducing the sample. I mean we can have a faster detection. So that the motivation why we are research on why we are going to direction on the lab on chip. But in my lab, we because we try to make it the costing and also the functioning, we work to the lab on printed circuit board. So this is, so when we talk about the lab on chip, what the component that we need. So normally we need the inlet. So that means to insert, I mean to insert the sample and also the reaction. So when the fluid is inserted to the fluid, and then we use a micro pump, so that can the fluid, the sample will flow, and then they come to the reaction to make it a mixing. That means to do the reaction. That means to make it a mixing between the sample and like the and a reagent. So that when they do a mixing and then they go to the reaction chamber to make it the detection. So then the signal will be amplifiable by the CMOS any the sensing interface. That means to have to amplify the electrical signals. So that's what the components. So I mean we need the micro pump. That means to control the flow rate, to control the amount, and then we need the mixing. I mean to do the mixing between the sample and a reagent, and we need a reactor chamber. What the purpose of the reactor chamber? To make it the detection, to make it the detection, and then being convert, and then we need the CMOS sensing interface to convert the signals. That means the chemical phenomenon. That means to amplify the electrical signal from the sensors. But for today, what I'm going to explore with all of you, with participants, how in my group we are focused on the droplet structures, why, and also the mixing, the mixing and also the reactor chamber. So that the today topic that I will go through with you. That means how we apply the soft lithography technique to develop the microfluidic channel, and how we apply the sensor on printed circuit board to have a sensing chamber. That means to have a complete system on the mixing and also the sensors. So when we talk about the microchannel, so like my lab, we are focused on the development. We are focused on the development of the microfluidic using the lithography technique. I mean, we using the lithography technique. So when we talk about the lithography, so we have a few methods. The conventional of lithography, such as we have like the electron beam lithography. So this is a latest. Now, when we talk about the electron beam lithography, it can go to the small pattern. It is going to fabricate until less than 5 nanometer pattern, but it's considered as a low throughput. And also they also have the laser direct writing. So it's one of the method how we do the patterning to create the molding. And then of course the currently we have a 3D printer, the 3D printing technique. So this one of the very attractive approach, but current is still a limit of the small patterning. That means towards to the nanometer order patterning. And also they still have a problem if you see the surface of the mold by the 3D printer, they have the roughness. I mean, we need some study, we need to mix with the acetone during the printing. So that means to have a smooth, the smooth mold that used to fabricate the microfluidic. That means to fabricate the micro channel. So that what the current available. So mean we have the electron beam lithography, but for the electron beam lithography, they have also a direct patterning technology, but also some technology we also need a masking. So that means it's a more complexity, is the low throughput. So how so it means because when we talk about the microfluidic, from some the biologists also, the chemistry also, they also can using the technology, that means to develop, the microfluidic. But what is the best method? Even though if the chemistry, even though the biologists, without the we have with some not a depth knowledge in the fabrication, in a semiconductor fabrication, but still be able to do the microchannel fabrication. So what our lab focus is, we try to focus on the what we call as a grayscale lithography technique. So the grayscale lithography technique, we are going using the grayscale with by control the percentage tone. That means the percentage tone of from the real white to the black. I mean, by control the percentage, how we be able to have the 3D structures and using a single masking. So that what is that mean the current, the motivation, the direction on in our group. So I mean we are going to using the grayscale. That by using the grayscale, how we can using only a single masking, but we be able to have a 3D structures. So that can be used for as a mold for a micro channel fabrication. So going to that, so when we go to the current technologies on the photolithography, they only be able to have a 2D structures. But if you want to have more like a 3D structure, mean they need the multiple layer and the multiple process, like have to do the etching, and then after do etching, they need do the deposition, but they need the more than one masking, right? And then the current available in the microfluidic fabrication, so we are difficulties. We have difficulties to make it the solid object that can be float in a micro channel. Because we have one recent a project how we work with the group from photonic. This group, they provide us the fiber optic, the taper optic, but the taper side must be float in the microfluidic. So must be float in the microfluidic channel. So that means we need have the multiple thickness. We need have the multiple thickness structures of the micro channel on a single subset. So that means we need, the higher side must be have a holder. That means to hold the optic. So and then the third problem means how we can have the problem. That means to make it a super hydrophobic, to have the droplet. So that means to have to create a droplet even though in the oil solution, so that can be potentially to use for biomedical. That means for the biomedical diagnostic. So based on the three problem, so that means what is the low cost? That means the simple way to have a 3D structures by only using a single masking, right? The second, that means how we can have not a planar 3D, but the micro channel, they have the multiple height, so that we can have make it the floating object in the microfluidic. For example, like our case for the development, the optofluidic. And then how we can using the grayscale technique and then to create the super hydrophobic to have a good droplet structures, so that can be minimize the sample during the diagnostic. So that are the three problem. So that means the three driven the motivation. So that we are going to explore that what we call the technique of the grayscale photo lithography technique. So that to make it the 3D structures only using a single masking. And that by using this technique, how we improve, that means how we can apply on the fabrication on the optofluidic and to develop also the droplet and also the mixing, and then how we do the integration with the printed circuit board to be as a rectal chamber. So this the methodology that normally what we use in my laboratory. So we have, so first we need to develop the grayscale photomask. So the grayscale photomask. So first we have to we using the AutoCAD software, so that we draw the pattern that they have the gradient of percentage. I mean the colors. That means the percentage from the total black and then to the white. Right? So and then so after after we do the printed, that means we design and then we printed on the on the transparent, so that the on the transparency of film. So from that transparency film, and then we use our mask maker to transfer the pattern on emulsion mask. Right? Then after we do a transfer on the emulsion mask, and then we do the development and the risk, and then we can have a masking. So the masking that we use with that from Konica, so that the emulsion mask. So the first step, we use any the AutoCAD software. Then that we printed on the transparent using the high resolution printer. Using the high resolution printer, so that we using a mask maker. That means to transfer the pattern that we printed on a transparency on emulsion mask. That means to have a masking. So that we do the development and then we get the masking. That we go to the SU. That means we go to the lithography process. So this lithography process. So in my lab we use the SU8 as a negative photoresist as a board. So we using the SU810 and then we do a spin coating and then we have a soft baking and then that we have a glass and the SU8. So from that, so we from the masking that we fabricated, so that example like a masking, then we can see that the masking they can have a different tone. So mean they have a different tone. So with a different tone, so mean they we have a different UV penetration. So that fabricated on single mask. So this UV is a totally blocked. So that's why they still remain the SU8. So what we using the substrate penetration lithography technique. So this is our glass. So this is the SU8. So we have the substrate penetration technique. Right? So here, so like this area we have a certain percentage. That means the UV can penetrate, but no, it's a less compared to a totally no black. So that means by using the different tone, that means the different gray tone. So we can have the multiple structure of the mold on a same substrate by using a single masking. And then after we do, so that we call as the grayscale lithography technique. So after we done the exposure, so then we go to the development and then we can have the SU8 mold on the glass. So right now in our lab, we can do not less than the 20 micrometer because the limitation of our facilities, right? So, and then, so after we've done the mold, and then we pour with the PDMS. So with we have a fit the ratio 1:10. So that we do a cure and then we peel off and then we can get the microfluidic, the micro channel. So this is the process that go through in my lab. So in our group, we are focused how we can apply the grayscale technique, the grayscale technique to have the multiple structures. That means the multiple height on a same substrate. So after we do the grayscale fabrication using the mask maker, then we do the lithography. That means to transfer our mask pattern on the SU8 mold. So that can be as a molding to fabricate the micro channel. So PDMS micro channel. So this is what we the real photograph. That means the image of our what we call the optimized recipe. So that the pattern from the 98%, 96%, 94%, and also like the 10%, like the 0%. So this is from the OSP. So this is transfer on the emulsion mask. So this our masking. That means from the mask we can see like so this is what the first step we want to have to see the optimization, how the related between the percentage of the grayscale, how we can correlate to the thickness of the SU8 mold. So that is the first step. We have to find the optimized recipe to have the preliminary data. So this data can use for the next step to fabricate the microfluidic. So this is some. So there is some the result. So we published in a micro machine journal, in a micro machine journal. So this that a different exposure time, and then we can see how the effect of the exposure time effect to the thickness, and how the different the grayscale. That means how the different, like the how is it they have a 58%, is it a different with 54, and then because to have the the recipe, to have the recipe, that means how we can relate the percentage with the thickness of the SU8 mole to proceed for the next any the micro channel fabrication. So by using that technique, mean we be able to have a multiple height of a molding on a same structure using single masking. So in our lab, we use the eye line. So with the wavelength, the 365 nanometers. So I mean we use the SU8 as our molding for microfluidic channel. So by having that recipe, so how we apply one of the application to develop the optofluidic sensors. So this work, we do a collaboration with our partner, with University Putra Malaysia at Kuala Lumpur. So their group expert in the photonic. I mean, their group they do a study on the fiber optic. So they create the fiber optic, the taper fiber, with the fiber, the taper size only the 6 micrometer. That means it's a very small taper, right? So we have to ensure this center must be a floating in a microfluidic, and then this part, so this part must be hold the optic, and then we have to, and then only this area so must float in a micro channel. So because they going to using this technique for the dengue detection, because around the optic they immobilize with the single standard. That means with immobilized with the amine, and then they will attached to a protein. That means to the dengue. That means for a dengue detection. So it means they need so this channel must be a close. That means they can minimize the sample of diagnostic, and then they will avoid the scattered of the optic during the detection. So that's why the one, so I mean in my group, so how we be able to have the micro channel, but not a planar micro channel, but the micro channel they have the multiple height. So that be able to us to hold, that means the inlet and the outlet to hold the optic only at the center part must be a floating. So by referring that the optimized recipe that we did, so that we have the grayscale. That means with a 66%, with the 66% at the center is that means the 70% and then 70%. So that means we can have, so that means to have the mold to develop the microfluidic channels. That means the channel that have the multiple height to embed the taper optic, the taper fiber optic. So in that one we did, so mean we have to seal with that the top PDMS and the bottom PDMS, and then need to have a handling. So it's really difficult. That means we develop the tag. That means to hold. That means to embed the taper fluid in the bottom PDMS, and then how to seal, and then how we can using the oven, the heat, that means to cure the sealing process. So that is the so that after we did, and then that means how they set up for that measurement. So that means that's our microfluidic channel that already we embed the fiber optic, and then we do a oven to cure the sealing between the PDMS and PDMS, and then we have the channel. So that's indeed so in the channel we embed the optic, and then we do the measurement to see how the functioning. That means the is it the in terms of the refractive index measurement. So this is one of the applications that we to work together with our partner with the that UPM, the University Putra Malaysia, under Prof. Adze Group. So this is what we can see. So mean when we do a cross section, that means we do the SEM, and then we can see that the taper lah. So that means that the taper. So I mean that see as a fluid in the channel, and then we move forward on the measurement of the refractive index. So this data we publish on the sensing and biosensing research in 2017. So that's one of the outcome. That means how we apply the grayscale for the optofluidic sensors fabrication. So this is one of the output that we have. So it means we use the potassium chloride as a test sample, and then we can see we change with a different concentration. We change the different concentration like the 0.1 molar concentration, 0.2 molar concentration, and then we can see they have the wavelength shifted. So that means by using by evaluate the wavelength shifted, and then we translate to the analyze on the how we correlate the wavelength with the refractive index. So this that we get the sensitivity is about the 1409.3 nanometer RU. So if that can be like the comparable to the micro scale in that published at the 2014. So that some one of the applications. So using the grayscale, and then we can have the multiple structures on a same channel, so that we can encapsulate between the PDMS and the PDMS, right? So then the next how we apply the same the grayscale, but towards to the superhydrophobic micro droplet implementation. So in this group, in my group, so we are focused on using the KC Baxter, the fundamental of the KC Baxter. What we from the KC Baxter, so Wenzel and the KC Baxter, their understanding in terms of fundamental. So if we have the 3D structures, so that means if we have a 3D structures, and then by do the arrangement of the gap between these 3D structures and this 2D structure, that means we create the air pocket. By creating the air pocket, actually we able to have to create the superhydro, that means to have the droplet structures. So mean if we can have the changing of the geometrical dimension, that means if we can control the pitch in the height, so we as a hypothesis we can have a super hydrophobic droplet. That means the higher contact angle. So that's what did what the referring on the Wenzel equation. But here we using the Casey-Baxter equations, and then to have, that means to develop the droplet structures using the formation, the changing of the geometrical dimensions of the nanostructures, I mean of the 3D structures, and also the pitch. So that's the how we did. So I mean we still we using the grayscale. I mean we have we create the micro hole. I mean the array of the uh the 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 SUA, and then we have the then that can be as a mold, and then we insert. I mean we use the PDMS to create the micro filler, and then we do the contact angle measurements. We do the contact angle measurement. But here's how we improve in terms of the super hydrophobic. So actually we have, so I mean from the we win from the SU8 hole, and then we create the SU8 micro filler, and then so we do the replication. I mean from the micro filler, and then we have the replication of the PDMS as a micro hole, and then we have a double again to have a micro filler. That means to be the replications on the micro hole, and then we see how the contact angle. I mean that one of the technique we do for the super hydrophobic application. That means to have a super hydrophobic droplet. That means the higher contact angle. So this is the pattern. So we do the patterning on our on the same on the transference, and then we transfer to the masking, and then we in this for the droplet we do the different grayscale. So we use the 92% and others, and also the 62%, and then we try to we have the multiple structures. That means in terms of the square shape, the circle shape, and then but also we have a changing on the arrangements of the filler. That means the arrangement of the mold. So there is the arrangement same, but here we change the multiple. I mean we change from the row and the row, and also like it's like a comb structures, and then we can see which can give a better hydrophobic, right? So this is what from what we done. So we have the fabricated. So mean we the same. So we have the glass on top of the glass. I mean we fabricate the SU8. So that can be the micro hole, and then we pour the PDMS. We pour the PDMS, and then we peel off, and then we can have a relief. So that can be the micro filler, and then for the super hydrophobic we insert in the PDMS. So that can be like the concept like the nano stamping technology. That the last 2 years they hot topic about the nano stamping technologies. Right, so that we have the few, that mean 1, 2, 3, 4. That mean the multiple variation of the arrangements of the micro filler. So and then from this device, so we use this instrumentations. I mean to do the for the contact angle measurement. I mean to see how the the conditions. I mean, is it they how is it they have a hydrophobic or the super hydrophobic? So how they are set up? So that we did at the UTSM. So at Johor. So that we have a water pump, and then that we can have the light source, and then we do so that we allocate our samples. So that we drop the fluid, so that the fluid, the image of the fluid we capture by camera, so that we analyze on the PC. That means to do the contact angle measurement. So that is some. Also, that is did at the U that I will at the USM. So that we have. So mean we have this. So the camera, so that we capture the multiple image. That means to do the measurement of the contact angle. Right, so this is from the SEM image. So we have a 200 micrometers and the 100 micrometer and the 80 micrometers. So the shape is a super high that the square distribution. So of course, because when we do the so that the SU8 micropilla, so that and then one we do the replications for the PDMS microhole, and then we have a double the replication of the PDMS microfillar. So that means, so from this part, so we can see if the structures here, so with the 200 micrometers and the 100 micrometers, and compared to the 80 micrometer pitch, that means we can see that they will increasing. That mean from the Casey Baxter, so that means they have a more the air pocket, so that increasing the contact angle, so that we reach until to the 157.3. So why we are going to develop this? Because if you talk about the diagnostic biosensors, some they need the droplet formation. So our motivation is, so we want to have the channel that in the channel already have the roughness. That means the 3D structures. All right. So during the fabrication, so we already can fabricate direct the channel, including with the modification of the surface. Right, so that is one of our so we have, so by implement, I mean the technique still using the grayscale lithography, but we have the replications of the PDMS microfillar. Actually, we be able to increasing the contact angle from the 153.2 to the 157.3 contact angle. So this is the shape is a square distribution formation. Right. So the next, actually, we do also some the others. They mean the hexagonal, that the like a comb, such as the hexagonal distributions, and then we see how the formations. So it mean the others, so that we can have some similar. That mean the same. That mean the contact angle, so that can increasing to the 157. That means that increases to about nearly to the superhydrophobic. The superhydrophobic, some definition is must be more than 160 angle. So that we call it the superhydrophobic. So what we get now is the nearly to 160 is 157.3 degree, right? So and then so that what we done. So the micro droplet, so the micro droplet structures, so that can be used to for into the for the applications. I mean the applications, any microfluidic that are needed, that are need any droplet formation during the flowing. So that is one method. So I mean we can using the grayscale, and then we can have the formation of the SU8 with the square shape arrangement by control the pitch, so that we also can have the droplet structures based on how much the contact angle that they are needed, right? So the next, how we apply the same for the grayscale, but towards to as a micro mixings implementation. So when we talk about the micro mixing, of course they are depend on the Reynolds numbers. That means we rely on the geometrical dimension. So that means we need to have the turbulent flow. So but when we talk about the microfluidic, of course when we talk about the microfluidic, then we behave the dynamic will behave as laminar flow. That's why how to make it, I mean how to have the turbulent flow, mean we need to create a more disturbance, the disturbance structures in the channel or any the geometrical shapes structures. So this is the hypothesis, the theoretical. So but in the dynamic, in the fluid dynamic, if you have a microfluidic, of course they will behave as a laminar flow if you have a planar microfluidic. So in my lab, so how we try to focus, so I mean we design is a 40 millimeter channel length and then 60 micrometer width, because how to have a mixing, I mean how to have the mixing structures. So that is a few pattern that we design. So I mean we have a few, so a few shapes. So we have the B, the B spline shape, and then we also have how in the micro channel they have the multiple step. Mean when the fluid come and then we have the multiple step structures. I mean that can create the disturbance, so that hopefully it can increasing the mixing ratio, right? So that we from this analysis, so this we based on the previous papers, the one of the researchers. So that means we using their structures and then how we implement using the grayscale to develop the structures. That means to develop the microfluidic channels, right? So in this, so we have the depth. We try to make it about the 500 micrometers, and then we using the four multiple percentage. That means like the multi-step, so we have like 62%, 72%, and 82%, and 92%. So mean that a few the structures that how we do. I mean we are going to develop the micro channels. So the first we just develop like the zigzag pattern. So that means that they when the channel come in and then because they have to change the shape of the flowing, that also can be effect on the mixing. Next, we in the channel we create the multiple step. We have the multiple step, and then to make it the disturbance, to have a turbulent flow. And this, we have the channel, but between that, we have like the island. So I mean, when the channel come in, I mean, they have need to concentrate on one area. So that hopefully also can have the mixing, right? So from this need, so we do the same. We have a software masking. We do the same technique with a droplet, the same technique to create the optofluidic structures. So we have, that is the plane structures. That the plane structure. Then we can see that the mass lah. So that our S you add more, and then that after we release on the PD by using the PDMS. So this is a same, but we have the multiple step. So we have the multiple step along the channel. So that means using the single masking, that we using the grayscale. So I mean, we have a mold, but they have the multiple step. They have the multiple step. So, and then here's, they are different. So we have the channel, I mean, but they have a caving. So that means they have a different, but they have like the cavity. So that the channels. So the the formations of the micro formation of the microfluidic. But here's, we have a two more. Mean we have the one more, and then to have a step here. But we have a that will be Spartan. So I mean, they have the channel. So that means they have a the obstacle. So that can have mean to give more obstacle to the fluid during the flowing. So that we have, and then we do the sealing on PDMS. That means we do a sealing on the PDMS and PDMS using the PDMF sealing process. So that's the setup. So this a setup we did at our collaboration at the UTSM, at Johor, at the Southern, at the UTSM. So we have the micro strings. That means to insert the fluid to the inlet, and then that they have the micro mixers, and then that we take the image using the inverted microscope. That means to see how the mixing percentage, I mean how the mixing condition, right? So this is the SM image. So this is the bare. There is a planar SU8 more. There is a planar SU8. So this is a second. So we have the structures. That means they they have the like a gap. So that means they have a different thickness. I mean they have the height. They have a 5,040 micrometers. Yes, but here they have like the cavity structures, right? So this is the others. So the final. I mean they have the multiples. I mean they so there is a few the from the SM image we can see how they have the multiple. I mean the multiple height like the 667. So from this view, this view card, and then we can see how they have the different step. So that means that how, so this we can see some in the applications that we only using a single masking, to have the multiple height in a micro channel. So this technique actually we done published on the last years in the 2020 in a micro machine journal. So that in the volume 11. So that we done we published in the micro machine journals under MDPI. right? So this some the result that we got. So mean we have these structures. So but these structures actually they have, we combine the multi-step, like the Y structures, and also have the multi-step. So it mean we do the measurement. So we insert the red dye and DI waters, and then from that system we can see how they're mixing, and then that we done at the outlet measurement at for the mixing, for a mixing percentage. So how we do the calculations? Yes, I mean we assume so the absorbent we with proportional to the concentration. So we based on the Beer-Lambert equation. So it means that is the DI water. So it means the DI water that is for the red dye, the absorbent for the red dye. So it means if they along the channel, mean they have a mixing, so that means they will reduce the 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 outlet side, we the absorbent will be reduced. So that what the inlet. So like the red color is about 1.4.4, right? So that the inlet, that the outlet. So that means when we see at the outlet, like the 3D serpentine, they have the absorbent less than from the 1.44 as at the inlet, reduced to 0.74. So when we do the calculation, we can see at a 55.2%. So so how we consider a mixing when the outlet must get achieve 50%. So if they achieve the 50% of the absorbent value, so we consider they completely mixing. So I mean they reduce from, I mean the DI waters, because we have the DI waters and the red dye. So I mean it's a fully mixed. So the total mixing percentage that must be a 50%. So that from that analysis, so we see the 3D serpentine. So with the zigzag structure with the multiple step, they give the highest mixing percentage compared to others pattern, right? So from this implementation, so we apply the grayscale photo lithographies, and then to have a various thickness of the mold on a single substrate, and then we apply for the fundamental study for the reflective index sensor application toward the optofluidic application, and also to using the grayscale to develop the higher the superhydrophobic we achieve 157.3, and also we also some work and the proof using the grayscale, and then to have to develop 3D structure. I mean the 3D structures of microfluidic, that we can have a good mixing ratio. So that is, so from that mean we be able to have the mixing a component, and we be able to have the droplet component, and then how we can apply for the sensing application. So in my lab, so actually we are focused on the electrochemical sensing. So we apply, we using the chemical sensing, and then how we do the fabrications on the PCB, on the printed circuit board. One of our current sensors, that mean the sensing principle, we using the electrochemical sensing, and then to develop for the one of work, that means to develop for the current work, that means for the heavy metal sensors. So that our PCB, so we using a normal printed circuit board that available in the current, I mean the available technique in a for a printed circuit board. So we started do the analyze on the geometrical effect, because the most importance for the electrochemical sensor is a working electrode. So that means right now we have a two type of the electrode. So we have a pure gold electrode and also the graphene oxide electrode. So why we have a graphene oxide, that means to make it that means to increase the surface area. When increasing the surface area, so that means they will increasing the current, because that the current will be one of the, we need to have the oxidation and also the reduction current. So that we do the fabrications on the fabrication process using a normal PCB, and then that we do the modifications on the working electrode with the right now we using the RGO, the reduced graphene oxide, and the graphene oxide as a working electrode, right? So that we but in my group we are really focused how we design, that means the geometrical on the counter electrode, how we can relate to the working electrode and the reference electrode as silver chloride to have a good properties for the as an electrochemical sensors. So this is our sensors design, so done by my PhD students. So we have the final design. So we have, because we have the design rules. So mean the counter electrode must be bigger than the working electrode. I mean to avoid the corrosion during the detection, right? So this is what our the layers on that case. These cases we use the FR core. That means the normal rigid PCB. We have a copper and a nickel, and then we have the gold, and then we have a silver. That means for the reference electrode. So that is the reference electrode. So this is a working electrode. So this is a counter electrode. Right. So for the silver part, actually we do the plating, the plating technique. That means do the electrode plating for a silver deposition. So this is what our the current fabricated the electrochemical sensors, and then on top here we are going to that mean that so we are going to have the silver, and then this working electrode we modify with the GO and also the RGO, depend on the any application, depend on the target applications. So at the end, so based on our study on the previous on the size, that mean on the mixing, that mean we do the integrations with the PDMS. So the microfluidic, actually we do the fabrication based on what the previous study using the grayscale lithography technique, right? So that what we, so some the SM image that we for the gold, and then that for a silver, and then that is for a GO. So this some the fundamentals. So we can see by using that fabricated on the PCB, then we can see they have a good the anodic current and the cathodic current. One of the criteria, the value must be a unity. The cathodic current and then the anodic current, the cathodic must be the unity. This is the criteria how to confirm your CV, your EC sensor is working. So that can be our platform. So that we using for the heavy metal detections. We test to the lead, the plumber. That means with a different concentration, so we can see they be able to do the detection for a plumber. And also right now we also working on the tripod, but we do the modifications on the working electrode, the working electrode, and also on the receptor. So and then the others we also fabricated also the same technique, but we for the PS sensors, and then we published last years on the in the sensors and materials. That actually we managed to get that the 8.3 millivolt per PS lah. So that the 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 sensitivity for the PS sensors using on the printed circuit board. So and then so the others we also explore other than rigid PCB, how the applications on the flexible printed circuit board. So this is what we did in my lab. So we also do the optimization. So this is the TPU, the Teflon polyurethane substrate, and then we do a simple circuit formation. So this is on the TPU. That on the PVA, the polyvinyl alcohol. So this is that is the PDMS. On top of the PDMS, we printed the conductive ink, and then we can see how the changing of the LED light when we do the stretching, right? So that is some also we did some tested also on the gelatin, the gelatin subset for a printed. So this is a printed carbon, the conductive ink. So this is one of our studies how we are printed on bandage, because we are going to using this concept how be able to develop the smart bandage. Mean the bandage have the sensors so that we can have the objectively measured for a smart bandage applications. So the bandage we buy from the pharmacy, and then we try to print the capability for the ink printed. That using the print screen. That means the print screen and using the inkjet-based printers. So right now we also are working with Japan, with Waseda University towards to the development of the printed on a printed the electrochemical sensors. So that is some so me the same concept is same.
Yes, sir.
The printed circuit board, but we change from the rigid to the flexible PCB. So this some news on in the 2016 how the first we do the episode on the with a company with a Japan. I mean that how they do the printed on the TPU, right? So by that, so hopefully by having that printed circuit board technologies from the rigid to the flexible, and then by do the integration with microfluidic, hopefully we can have a smart system application for the biomedical application or any the applications on the for a healthcare specific for the precision medicine applications. So as summaries today, so actually I give you the exposure how we apply the grayscale to develop the microfluidic using a single masking that we are tested on the droplet, on the mixings, and also the application on the optofluidic, and how we integrate with a PCB technique to create the reaction, that means to create the sensing region. So we are tested for the PS sensors and then heavy metal, and we are ongoing on the tripod on the cancers, the electrochemical for the printed, for the flexible printed sensors. So this is an overview item for the UPN, the collaborator, and work for the France and also from the Japan, and also for my PhD student done already graduated. Then that's the ongoing students for my project. So that if you that's our publications. So that we are related to the lab on PCB and also on the microfluidic fabrications. So that I will share you is it the video that done by my PhD students. So how the step how we did the microfluidic, the micro channel fabrications. And then the next video I will show to you one of our printed flexible electronics. So that what we have in our lab. So actually we collaborate with the chemistry from the School of Material. So they we provide us the ink, and then the ink accommodation. So we do a direct printer on the PCB, and also we work also on what I just shared with you on the TPU, on gelatin, and also on the others, uh, the the substrate. So that what we have in our lab. So that is the print screen. So this is the inkjet based printers. So actually we also work with the expert in the chemistry. That means to provide us that the ink, that is a CNT ink, the carbon nanotube ink. So that we insert in our the cartridge. So we try to develop a circuit or any sensor. So that's on the TPU, the TPU subsets. So that's all from mine. So I hope so. Thank you.
Thank you, Dr. Asrul sir, for your very wonderful presentation and the research activities you have exposed. What are all the research activities going on in your lab? The video was very much interesting. Usually, I used to hear from our Dr. Yusuf, but it was very quite interesting if I see that videos and all. Even though I'll be something deviated from this stream, but the research works are very interesting. Now it's the time for the participants to interact with the speaker, to have your queries. Now it's time for the participants.
Good morning, sir. Can you able to listen to me?
Yeah, can.
Sir,
good morning. Yes, yeah.
Do we have any open source softwares to design these chips?
What?
LOC design. Open source softwares.
Software. The software. Okay, so I mean actually if you want for the design, that means for design the software, that means for to design that we using the normal or the AutoCAD software to design the geometrical dimensions. So that we use a normal AutoCAD lah. That means to design, but to do the simulations on the microfluidic behaviors. So we use the ANSYS and Fluent. We use the ANSYS and the Fluent that for the finite element analysis modeling. So that to see the fluid dynamic behavior. But to design the pattern, we using the normal AutoCAD. So in my lab in Japan, we use the Adobe Adobe Illustrator, but here we use the AutoCAD. That means to design the pattern. But for the fluid simulations, for behavior, we use the ANSYS and the Fluent.
Any other queries from the participant?
Sir?
Is it I answer your questions?
Yes, sir. Yes, sir. Any more queries from the participant side?
So for my lab, for a fluid, for the microfluidic, actually we have a two software. The first software, that means to design the pattern. To design the pattern, actually we use the AutoCAD. software. But to do the fluid modeling, the fluid simulation, we use the ANSYS and the Fluent.
Okay, I think there are no more queries from the participants. If you have any queries, so the speaker will have provided the email ID as well as the contact address. You can personally approach the speaker also.
Yeah.
So
Thank you.
very thank you, sir, Dr. Asrul, sir, for your excellent presentation. Really, the presentation was very quite interesting. I was listening for the continuous from the beginning of the session. It was very interesting. So on behalf of our college management as well as the organizers, I thank you once again for this excellent presentation as well as your research activities. Thank you,
Thank
sir.
you
Thank
for invitations. Thank you.
Thank you, sir.
Yeah. So the last for me, the stay safe and take care. Bye bye.
Thank you, sir.
Yeah. Thank you. Bye.
And a small instruction for the participants. Due to the Friday prayer commitment, our next session will be by 2 p.m. Actually, for the past 4 days, the evening session, the afternoon session started by 1 p.m. But due to this Friday prayer commitment, our next session, afternoon session, will start by 2 p.m. And the session 15 have been specially allocated for validatory as well as the feedback session. So after the discussion with our coordinators, we thought that the 15th session will be clubbed along with the 14th session at the end. Okay, so no separate link will be shared for the validatory feedback. So in the 14th session itself, at the end of the 14th session, we'll be having the validatory function as well as the feedback. So I request the participant, those who are joining the 14th session, you try to be a part of the validatory function as well as and also you will be having a quiz also as well as the feedback session also in the 14th session. Now it's time for the participant. I request all the participants to turn on your video so that we can have a screenshot of the participants. I request the participants just to turn on your video so that we can have a gallery view of the screenshot. Thank you. Thank you. Few more participants can turn on. Few more participants, I request. Few more participants. We are getting only 10 participants screen here. Okay. Okay, thank you, sir. Thank you, speaker, sir, and thank you, participants. We hope you to join in the upcoming 14th session by 2 p.m.
Thank you. So actually, I share also my email address at the chat box. Okay. Thank you for the invitation. Thanks, and stay safe and take care. Bye bye. Thank you.
Thank you. The feedback for this current session will be posted in the Zoom chat. Participants can give their valuable feedback.
Sequence. Bom, acaba posso falar uma outra. Acaba já viu, né? Não chega.
अकाउंट को पैसा देख खल्ला वाला का क्या मैं खाता हूँ तुम्हें खा लो पहला
Ma'am, next session is by 2 o'clock only, no ma'am?